How about energy accounting?
Oh.
Yeah, he needs to do some energy accounting. And there are a couple of things that need to happen before he's ready to do his energy accounting. What does he need to do to his diagram to make it ready for energy accounting? Nope. You actually don't need to do any of that.
Find the potential energy.
Nope.
Just draw them. You need to figure out where the before is and where after is and put it on your picture.
Yes, and in this case, we've got it labeled before and after points A and B. Coordinates. We need coordinates. That has to happen on your diagram before you're ready to go. And that means finding a place to call 0.
A.
Okay, we'll call A 0. It's not the choice I would make, but it's not a bad choice. No? We'll go with A. And then if A is 0, then we need a coordinate for B.
Negative B.
Yeah, but can we get an actual number to it? I think we can. Yeah, that's right.
Oh, yes.
So we need to know this length right here. Everybody do that. Find that length to go.
Wait, and A to B is 75.
Mug him.
Mug me?
Yeah, you're getting ready.
Second time in 2 days that I've been
28.9.
Okay. We'll call it 28.1. So what does that make the coordinate of point B down here? What does it make the coordinate of point B down here?
0. Alright, 0, 0. Oh no, that would be 0, negative 28.
Negative 28.1. And we're only going to do the vertical coordinates because we're only interested in changes in height. Okay. So now that we've done that, now we are finally ready for our energy accounting. So how does it look? We're going to do the table. We're going to do the table at each point.
And you, wait, C is negative 28.1.
Yep. And then we're going to total it up. Okay. Give me potential energy and kinetic energy at point A.
0 potential.
Good. 0 potential energy. MGH, and H is the coordinate that we've marked. That's why we marked those coordinates.
Negative potential at 5.
Yeah, that's right. It won't mess anything up drastically. It's going to make it more annoying than anything. All right, what about the kinetic energy at point A?
0.
Also 0. Our skier has not gone anywhere yet. So we have a total of 0. Matthew, you ready to hit point B here?
Yeah.
What's our potential energy at point B?
Mass times gravity times height.
So what numbers can you fill in?
Gravity and height.
Go ahead. So what does it give you?
Full gravity and height would be negative 281.
Times n. Exactly so. So we end up with negative potential energy at the bottom. That's not a problem. It just means we're below 0.
What was the units on that, G?
Joules.
Joules, times mass.
Joules. The whole thing is joules. So it's kilograms times meters squared per second squared.
Right.
What about the kinetic energy?
1/2 v squared.
Yeah, we don't know what the V is, so this is the best we can do. And now when we total it up, we get 1/2 mv squared minus 281m. Now, question. Will the energy, the totals at A and B, be equal to each other? We're getting,
No, this was the mu.
because of friction, they will not. Friction is a non-conservative force that takes away energy from the system. So, we're going to have to add in the work done by friction like this. We're going to express our conservation of total energy like this. Initial energy plus the work done by the non-conservative force of friction equals the final. And now we pull all these values off the chart.
It wouldn't be minus.
We're going to end up with a negative sign for the work done by friction, but we are counting that as negative work done that we are adding in. It's a loss that we're adding. Equals, and this is going to be negative 281 m. Well, I need more space. Plus 1/2 mv squared. Okay. Well, this means that if I want to have any hope of finding V, that I need to find the work done by friction. So let's go back and examine. We remember that work is force times distance. So we need a frictional force. And now is the point where we need a free body diagram. So here's our sphere, and it's a pretty familiar free body diagram, right? Got a normal force this way, got a frictional force this way. We're going to have the two components of gravity, mg sine theta and mg cosine theta, all going this way. So according to this, what is the value of the normal force?
Gravity times the mass.
No. According to this free body diagram, what's the value of the normal force?
mg cos. Negative mg cos.
And the mg cosine theta, right? And therefore, what is the value of the frictional force?
Mu times.
Good. And so the work done by friction then, now let's see here. It's force times distance times cosine of the angle between, right? And the angle between those two is 180 degrees. The frictional force is pointing up the slope, and she's sliding down the slope. So the work done by her is going to be negative 1 times the frictional force times what distance does she travel? Good, 75 meters. It's not her vertical distance. And now I'm ready to put all this back into place here. Negative mu times mg cosine theta times 75 equals negative 281 m plus 1/2 mv squared. And we're ready to cancel our m's. And at this point, we have values for cosine theta and for g and for mu, so we can plug all those in and solve for v. You do that while I get Lindsay set up.
When you plug in mu and g and cosine theta before,
You can do that also.
is there like a reason to do it?
No.
I don't know.
When you solve for v, what do you end up with? How many words?
So you just do that in your head.
I get 14.8. No, I don't. hang on.
Then
forgot to add part of it,
actually
too.
right, if you took a total shot in the dark.
I was just thinking minus.
I got 20.9.
I actually did it in my head. I was thinking minus because
We're being modest. So what made the energy accounting a little bit tricky here was that we had to account for the work done by the frictional force, right?
Why is work equals force times distance? Why is it negative mg cosine?
So work is actually equal to force times distance times the cosine of the angle between the two, right?
And it's what?
And because your frictional force is this way, and your distance is this way, your angle is 180 degrees, and the cosine of 180 degrees is negative 1.
Okay.
There should be an intuitive gut check that you always do when you're computing work, and that is you should ask yourself, is the work done here positive or negative? Is it going to slow her up, or is it going to speed her up? Slow her down, or speed her up? Does that make sense?
Yeah.
Well, in part B, they ask about how far she slides this distance right here. Call this distance D. And so we're going to do energy accounting again. And when we do the energy accounting again, she is at the bottom, so negative 281 M. She has no kinetic energy anymore, so her potential energy is now negative 281 M. And so we ask, where did all that energy go? Well, I can keep track if I take a look at the energy at point B versus the energy at point C. Because the energy at point B we already computed was 1/2 mv squared minus 281 M. If I now add to that the work done by friction as she scoots across, then that gets us down to the amount of energy that she has at part C, which is negative 281 M. Algebraically, notice that we can immediately cancel the negative 281 M's. And we get something that makes a whole lot of sense, and that is that the work done by friction is equal but opposite to the amount of kinetic energy that she had right there at the bottom. In other words, she had a whole bunch of kinetic energy, and friction just took it away as she slid along the surface. Does that make sense to everybody? So, how much work was done by friction? Well, it's going to be equal to the frictional force, which is mu times the normal, times the distance d, times the cosine of the angle between, which is again negative 1, because the frictional force is pointing this way while she slides that way. And what is the value of the normal force? Quick free body diagram, and the normal force is going to be equal to...
Negative mg equals theta.
Yes, but what is theta in this case?
It's 22, right?
She's not on the incline anymore.
No, 0.
It's 0. What's the cosine?
Negative mg,
Negative mg.
which is negative.
Wait, can you go up a little bit?
Yep. And so we get, we know the value of V right there at the bottom. So we have 1/2 times 20.9 squared equals 0.09 times 10 times D. And the D that you get is going to be pretty large. I got 243 meters.
Or actually, 18,000.
That was close. So the key point here is that we account for energy at different points along the way, and the difference in energy at various points will be equal to the work done by the non-conservative forces. If you have no non-conservative forces, then the energy will be equal at all points along the way. And that's what we were doing with our conservation powers. Okay? Questions on that one? Let's talk power.
Wait, I want to. Can you go up to the top of the table? Up further.
Okay.
Wait, so where'd you get C from? Oh, wait, just C.
Where did I get C from? Well, she is on the ground, and in your coordinate system, the ground was negative 28.1. So our potential energy is mgh, which is going to be mg times negative 28.1. Yeah. You can see why usually people will take 0 to be here. Yeah. It simplifies your computations. But having chosen a coordinate system, stick with it. Okay? All right. Let's talk power. When we're talking about power, we're talking about the rate at which energy is delivered with respect to time. In other words, power is equal to the amount of work delivered per unit of time. Now, if we think about the units here, the units are measured in joules per second, right? Energy over time. It does. 1 joule per second is the same as a watt, or the abbreviation W.
Was a Newton meter per second. That was a lot.
No, a Newton meters squared per second cubed.
Oh, it's a Newton. Isn't a Newton something too?
A Newton is a kilogram meter per second.
Okay, kilogram meter per second squared.
Meter, sorry, Newton meter per second. Right. So a Newton meter per second is a watt, and that would be a kilogram meter squared per second cubed.
Okay.
Which is totally worthless.
Lots per second.
There's also a unit of power called horsepower. And in your reading, you will discover how many watts a horsepower is.
And so a watt just like 10 watts of horsepower or something.
Something like
Yeah, I
that.
thought it was
Not like watts.
More than
or
that.
distance or something.
24, I thought.
Well, horsepower is just another unit of power. Now, where have you heard of watts before? Light bulb. Right. Immediately everybody says light bulb. What other units, things get measured in watts? Electricity, electrical stuff in general, right? Anybody use a hairdryer? Use a hairdryer. Lindsay looks around just like they're all boys. Hair dryers are measured in watts. About 1,500 watts for a hair dryer. About 1,500 watts for a refrigerator. About anywhere from 2,000 to 5,000 watts we discovered.
So you can measure.
That's ridiculous. You could measure your hair dryer and horsepower. Oh my gosh. A couple of horsepower. Couple of horsepower for the hair dryer. Your central air conditioning is the thing that uses the most power in your house. 2,000 to 5,000 watts. 2,000 to 5,000 watts. Yes, that's exactly it.
Oh, that's a lot of watts.
Now, speaking of, what's that?
It's
Uh-huh.
700.
Oh, that's meters squared, kilograms, grams, second.
Kilograms or meters?
Okay.
Kilograms.
Now, this unit you're going to see a lot of. How many of you have ever gone outside and looked at the power meter in your house? A couple of you have. Okay. All of you, you have an assignment for tonight, and that is to ask your parents, where is the power meter in the house? Go outside and look at it. And you should see a little dial that's spinning around, and as you look at it, it should be labeled in kilowatt hours. So you say, what the heck is a kilowatt hour? Well, actually, we can figure that out. Because a kilowatt is going to be 1,000 joules per second, right? And if we now multiply that by 1 hour is how many seconds? 3,600 seconds. Then we get 3.6 times 10 to the 6th. Oh, look at that. The units are joules.
Oh,
3.6 times 10 to the 6th joules. It's just a unit of energy. A kilowatt hour is a unit of energy. And it's a yes, it's called a kilowatt hour. And if you think about it, this is a humongous amount of energy. If we took a 7-ton object and raised it to the height of the school, it would have a potential energy of about 3.6 times 10 to the 6th joules. Think about how much human labor it would take to take a 7-ton object and raise it to the height of the school. You get all these ropes and so on and so forth, accelerate, pull, and everybody starts pulling, right? It would require a large percentage of the student body to do that.
And then you dropped it.
Yeah.
Else put on.
And it would take... Exactly right.
Wait, what?
If you dropped all of a sudden, you would power your house for an hour. You think that's funny, but it's actually true. We'll come back to that in just a second. So it would require a huge amount of man-hours, or effort, not man-hours, but it would require a large number of man-hours, I think, to raise that 7-ton object. This amount of energy right here, 1 kilowatt hour, when you buy it from the power company, they charge you about 10 cents. And that, my friends, is the Industrial Revolution. When we went to powering stuff by horsepower or human power and switched over from that to powering things by coal power, oil power, now we're talking about marine sources of energy like wind power, so on and so forth, that greatly decreased the cost of energy to us, so that we can now afford to put more energy into things, such as 1,500 watts for a hairdryer.
Yeah, you probably couldn't pay like 100 people 10 cents to like the 7-ton rock.
Yeah, you probably could not. Exactly right. That's exactly right.
And how many people would it take?
Well,
Well, if you got enough, you could just
7
counteract the
tons.
balance.
So
Pulley or something.
I figure I could probably cold lift, maybe 100 pounds, 150 pounds, somewhere in that vicinity. And so you would need 70 of me. No, what's that? 140 of me.
140, and you get like
Yeah.
100 cents
But
total.
could you like make a counterbalance for it? Or,
Well, you could, but that counterbalance would have to already be up.
yeah, but like you could make a counterbalance. So if you like put like 10 pounds of force on,
Oh, I see. You some kind of simple machine.
Yeah.
Is what you're saying. Yes, you can do simple machines to reduce the amount of force. The cost, however, is that you have to go a further distance. So you can actually never cheat the total amount of energy required.
well, let's say you have like a metal bar that's really high up with,
Yep.
and you're gonna throw a rope over it, attach a pretty heavy rock, like maybe an
Okay.
800-pound rock.
Yep.
Could you, I mean, I know it would take one time where you have to pull it up, then could you tie a rope to that one, tie a rope to like 750-pound rock on the other side of it, so it's enough to pull that, like that rock will still go down,
You can use some of that energy, but you still have to invest the initial amount of energy into it,
but then you can achieve your rocks.
and then you can use it. So in the other class, Heidi made a good point. She said, when you say energy, I think of electricity. Is that, when I say energy, is that the first place that you go, is electricity?
In part,
In part. Some of it. So then that allowed us to talk about the tie-in between electrical energy and mechanical energy that we've been talking about. The device that converts electrical energy into mechanical energy is called a motor. And so what a motor does is it consumes electrical energy and turns that into mechanical energy. So if I wanted to raise this 7-ton rock, I would hook up a suitably powered motor that's capable of generating enough force. And I would turn it on, and the electrical energy that I put into it, 3.6 times 10 to the 6 joules, would slowly be converted into potential energy of the rock.
So it's like
If I were to, thank you, if I were to now take this rock up at the top, turn off the motor, and let the whole system go, then the rock would fall, and as it goes down, the rope would pull the motor in reverse, and it would generate electrical energy off the back end. So a generator and a motor are really just the same device run in reverse. In robotics, you probably notice that when you turn the motor, it turns the lights on the controller. Have you noticed that? And that's because it's generating electrical energy. Yeah. Okay. Now, what sorts of computations do we do with this? Well, here is one example of computation. Let's take a look on page 164, problem number 58. And in problem number 58, they ask, how long will it take a 1750 watt motor to raise a piano of mass 315 kilograms, a distance of 16 meters. Now, to solve this problem, we don't necessarily need this, but I want to draw a picture so we can see what's going on. Here is my motor with a rope around it. We're going to have some pulley up here. The rope goes over. And here's my piano, 315 kilograms. And the wattage of the motor tells me how fast energy can be delivered, right? It's the rate of transfer of energy. So as this motor runs at 1750 watts, every second it's going to add 1750 joules of potential energy to the piano. In other words, it's going to raise it by a certain amount. And so we're really just asking, how long is it going to take for it to raise it the entire amount? And so we set it up as power equals work over time. And the power delivered by the motor is 750 watts. I'm going to write that as joules per second. Equals. And now the amount of work done is going to be the amount of potential energy delivered to the piano. Excuse me. Which is going to be mgh. Or 315 times 10 times 16 meters. All over delta T. And if I remember correctly from the previous class, that is 50,400 joules divided by delta T. This is the total amount of energy that it takes to get the whole job done. And I am capable of delivering that through this motor at a rate of 1750 joules per second. So do a little bit of algebra and solve for delta T. Go. Still do it on paper.
I think it's about 37.
20.
Yep.
I say it's about 30 seconds.
In other words, it would take us about a half a minute. Now, if I wanted to go faster, what would I have to do?
Put more energy in it.
Right. In other words, I would have to use a more powerful motor. So the power rating of the motor doesn't tell me how much total energy I'm getting out of it, but how much energy per second I can deliver. Now I want to do one more thing here that's very interesting, to give an alternate formula for the power. We go back to our formula, power equals work over time. And I want to rewrite work as force times distance. Let's assume that the force and the distance are in the same direction, which gives the motor its maximum efficiency, right? So the cosine theta is equal to 1. And if I do this, then I see that I'm left with this very interesting quantity, force times delta x over delta t. What's another name for delta x over delta t?
Velocity.
Velocity, that's right. So that we find a second relationship between power. Not only is it work over time, but it is also force times velocity. Now, the reason this equation is so interesting is that it tells us there is an inherent trade-off in anything that is powered. You can have a large force, or you can have a large velocity, but you can't have both. You can either go fast, or you can go hard, but you can't go fast and hard.
Why?
There it is. If you have a fixed amount of power, then you have to either put it into your force, put it into your velocity, or some compromise between them.
It's always huge trucks that tow things or something.
Exactly so. That's right. Huge trucks that throw things have to go slow because they are putting they're investing their power into the force rather than in the velocity. It's also why robots can either go fast or they can go with power that they can't do it.
You need to get a bigger motor.
Oh, in other words, could you increase the power? Right, you could get a more powerful motor, but given the motor that you're working with.
Yeah.
Increase. That's exactly it. Well, I'd like to take a look at number 64. How much work can a 3-horsepower motor do in a time of 1 hour? This will require you doing a little bit of looking things up and a little bit of calculating. Go.
What?
A 3-horsepower motor.
What's a horsepower again?
That's what you're going to look at. Do you have a phone?
Not a smart
An iPod? I know you have an iPod, but I'm asking if you have an iPod.
Okay, probably look it up on
Wow, you didn't know that way.
Wow.
Physics, come on.
2250.
All right, so let's look at watts. 2250 watts. That's the
That's for seconds.
Very good.
Energy or
watts
is
is
generated
joules
by like
times
a force running. That's what more or less than 1 horsepower.
3-1
equals
So it's actually like 1 point.
Yeah.
2250 equals 3600
Is that where they got the name from?
J.
Yeah.
I thought it
It's
was
literally the power from the forces were kind of the preferred energy source for about 400 years, right? And so, if you had a mill, for example, that mill would typically have 4 horses tied to it. They'd walk around, and as they walked around, it'd be storm.
In how much work?
So that would be 4 horsepower.
Hours.
Yeah, so that.
power is the noun.
So wait, could you play T versus turn around and just like put it in them running?
Like that's impossible to really understand.
I thought you weren't that.
They usually have them walk.
What if your character running?
So they would put it into, well, yes, but think about your trade-off, right? Horse versus speed. So if I could get away with 4 horses running, then I can do,
My students are really super.
Yes, they are.
well,
Okay.
Yeah.
So 1742.
Not 8,000.
8 million.
Because I just did 2279 times 3600. You can just make it like 2,000 times 4,000. It's like a million. So like a million.
all right, so what do you have? Let's see. What do you have?
We're still trying to get it. I'm not getting it yet.
Yes, but what do you have?
So one HP is about 746 off.
Okay, fair enough. So that gives you what? What are we talking about here?
So 3 times 746 watts.
Is what?
Equals 294 kilowatts.
All right, good. All right, so that reflects the,
30. It's 38.
38, okay. So that reflects the power of the motor. Now, what else do you have? True. So what formula do we have for power? We actually have 2.
Delta
Right.
So 2234 watts over 3600 second.
Because work and watts have the same symbol, which is really unfortunate, I'm going to write my watts as joules per second.
Watts and what has the same symbol?
And work.
Yeah.
They list-
Yeah.
I'm just horsepower, so it's like this tomorrow.
Yep.
That's gonna be on the test.
Yes.
Oh, I thought that is the one.
Latin.
That is the one.
Yeah, no, it's work, unfortunately. So how much are we talking about?
Oh, this is 0.622.
No way.
But that'd be closer to.
Plug that back in. 0.6 divided by 3600 is 2200.
It'd be like 0.
Oh, wait.
Alright, alright.
Work is like
Yeah, I
8
can
million,
take
right?
Yeah.
Wait, you did want to do
Seconds.
seconds or hours?
I thought the question called for it in hours.
The question gave you an hour.
What do you
It's time for one after announcement today. I'd like to ask everyone to please listen as we have an important announcement.
Okay.
Tomorrow, we are welcoming some guests to our buildings, parents and prospective students and chaplains. And we would like to ask everyone to please be aware of that.
That's 8 million, right?
Welcome them and let them know that you are